parceiros para desenvolver isso no terreno, mas não.
Mas seria a apresentação do serviço ou teria que ir no drone com a tecnologia?
Não, o Unicamp não desenvolve produto. A gente só presta serviço, né? Então, no caso, a gente buscaria parceiros para desenvolver e depois os nossos parceiros comercializam. Então, seria algo dessa linha.
Eu lembrei rapidinho, tá? Só para a questão do regulatório. Regulatório. Só para a questão do regulatório dos canais de TV. Eles sabem que o Wi-Fi, são 4, 5 GHz, são bastante liberados. Outra questão regulatória, a gente fala de instalar uma sistema básico na fazenda, a gente precisaria ter uma revisão do sistema de regulatório, para liberar esses canais de 900 professores para a gente não.
Os canais de TV são não licenciados, né? Então, teoricamente, você poderia usar. Né? Mas, nesse caso, nessa arquitetura, você está beirando quase uma linha privativa ali, né? Então, como toda lei privativa, você pode implementar, mas né, tem toda a parte regulatória da Anatel ali que tem que seguir. Seria nessa linha mais ou menos. De nada.
Obrigada. Bom, e queremos assistir a outra apresentação, vamos sobre os problemas técnicos? Sim? Hello, Oliveira. Please open your screen. Não só. Nós conseguimos assistir Osvaldo, eu acho que nós não conseguimos assistir nada. Oliveira ou Matheus? It's impossible in no presentation. What technical problem? I don't know. It's okay? 1 minute, please.
Hello, can you hear me? Good evening, everybody. Hello? Can you hear me?
What? It's okay? Okay.
Can you hear me?
It's okay, it's okay. Good evening, good afternoon. Is it start your presentation, please? It's okay? It's okay.
Can I proceed with presentation?
It's okay. Starting. Where is it? Present. Now.
Can I present?
Yeah. Starting.
Okay. Good evening. My name is Matheus. So I am here on behalf of the authors to present a paper titled Resource Constrained Federated Learning for Precision Agriculture using ESP32H device, a paper presented at the 2025 Symposium on Internet of Things. The paper were jointly co-authored by a number of authors here, but I am the one presenting it by name Ugochukwu Okudile-Matthew. Presentation outline. This is how this presentation was outlined from introduction to references. The agricultural industry is increasingly adopting advanced digital technologies to optimize productivity, sustainability, and decision-making process. Precision agriculture, a concept that integrates sensor-based monitoring, Internet of Things infrastructure, and data-driven analytics, has emerged as a transformative approach in modern farming. By leveraging real-time environmental and crop-related data, farmers can make informed decisions on irrigation, fertilization, pest control, crop disease status, and yield forecasting. Despite these advances, current smart farming systems are heavily reliant on centralized cloud infrastructures for data processing and model training. This centralized paradigm poses several challenges, particularly in rural or remote areas where network connectivity is limited and power sources are unreliable. Transmitting raw sensor data to cloud server introduces privacy concerns, increased energy consumptions, and latency issues that hinder real-time responsiveness. To address these challenges, this research proposes a resource-efficient federated learning framework to precision agriculture using ESP32 microcontroller. Of course, ESP32 devices are low-cost, low-power microcontroller developed by Express if system, widely used in Internet of Things application. It is also commonly used in smart agriculture, home automation, wearable technologies, industrial monitoring, and electronics and robotics. So it's an emerging technology. Federated learning in this context enables collaborative model training on distributed edge device to support scalable, robust model development across disparate agricultural sites while adhering to data protection and regulations. The system performs distributed on-device training on sensor data transmitting only model weights updates to a central aggregator. The aggregated model is quantized and deployed back to ESP32 device for real-time and local inference. Contribution of the work. This paper proposed and simulates a resource-constrained federated learning framework tailored for precision agriculture using ESP32 microcontroller. Design a centralized training pipelines where local models are trained on sensor data. Implement federated averaging to aggregate client update and simulate communication across each device with limited bandwidth. It also applies post-training quantization to compress the global model for efficient deployment on ESP32 microcontroller with limited memory. Evaluate the framework using a real-world smart farming dataset to determine practical viability for edge deployment in energy-constrained agricultural environments. Then the methodology that were deployed. This study proposes and simulates a resource-efficient federated learning framework for precision agriculture targeting future deployment on ESP32 microcontroller powered by renewable energy sources such as solar panels. A 5-volt solar panel powers a 3.7-volt lithium battery, 2,000 to 3,000 microampere to enable off-grid operation. The sensor array includes soil moisture, temperature and humidity, and light sensors. Down this paper, the figure 1 illustrates the hardware. That is the figure 1 referred to. We're looking at the methodology. It's a figure 1 illustrates the hardware setup showing the power and data flow of the off-grid solar power Internet of Things device for precision agriculture. That's in looking at the data collection and the model, the mode of its operation. If you take a look at this, this is how the methodology we are put together as a matter of fact. Then figure 2 illustrates the proposed system architecture. This is figure 2, the flow diagram of the operation of how this is put together. Okay, the figure 2 illustrates the proposed system architecture showing how the framework could be deployed in a real-world setting using ESP32H device, solar power for powering the device, and federated learning for data aggregation. Okay, this is the first stage of how the system was set up. It's looking at data collection and how the device were powered. Go further to system operation, looking at the resource constraint federated architecture for precision agriculture using ESP32. Okay, so this is how the system were put together. The data that were collected, the Internet of Things sensor data, you have the soil, the temperature and humidity, then being passed on to ESP32H device, then local model training, transmit model, wait. As a matter of fact, this is the flow of what was done here and how it was done. Then implementation. Data from 500 farms were collected, each treated as a client because it operates in a federated learning mode. Sensor control features include soil moisture, temperature, humidity, and rainfall, while user provided input include crop type, soil pH, and fertilizer use. Data was preprocessed by interpolating mixing values and normalized using standard scaling to ensure zero means and unit variance. Feature selection was performed with an ANOVA F-values based methods, aggregating scores by logical feature group to identify the top 8 most relevant groups for the prediction task. The selected features were scaled and their statistical properties documented. Finally, the data set was split into training and testing set. Of course, that is how it's supposed to be for validation. Client updates were aggregated using federated averaging, and resulting global model was quantized for deployment on ESP32 device. Evaluation focused on classification, accuracy, communication efficiency, and latency. Continuation with the implementation, the quantized model running on each client device provides diagnostic insight and actionable recommendation. to farmers, including irrigation scheduling, soil pH adjustment, and fertilizer management guidance. Client updates were aggregated using federated averaging, and the resulting global models was quantized for deployment on ESP32 devices. Evaluation focused on classification accuracy, communication efficiency, and latency to assess the system suitability for energy-constrained agricultural environment. The quantized model running on each client device provides diagnostic insight and actionable recommendation to farmers, including irrigation scheduling, soil pH adjustment, and fertilizer management guidance. Result and discussion. Table 1, this table 1 here referred to. Table 1 presents the classification performance of the model over the federated learning rounds with corresponding visualization in figure 3. The steady improvement in accuracy from 75% in the first round to 99% by the 10th round demonstrate effective model convergence through federated averaging aggregation of client update on ESP32 age devices. A significant improvement was observed in accuracy, precision, recall, and F-score across federated rounds, indicating balanced and reliable crop disease detection. This result validates the there are 10 rounds here, and these are the values being inputted and calculated as a matter of fact. Then this is the classification performance over federated rounds for crop disease detection. Has been implemented in this research, clearly defined and graphically visualized. Then result and discussion. Table 2, communication overhead per federated learning rounds in megabytes. Table 2 and its graphical representation in figure 4. Estimated communication overhead in megabyte transmitted per federated learning. Table 2 and its graphical representation in figure 4 represent the communication overhead per federated learning round, ranging between 0.05 megabyte and 0.06 megabyte with an average of 0.06 megabytes. This slight variability reflects intermittent power and connectivity typical to renewable energy powered ESP32 age device, causing fluctuating client participation. The consistently low data transmission confirmed the framework's communication efficiency critical for bandwidth and energy constrained agricultural Internet of Things deployment. Moreover, the federated learning approach inherently supports synchronous client updates, enabling robust model convergence despite real-world operational challenges. The consistently low data transmission confirmed the framework's communication efficiency critical to bandwidth and energy constrained agricultural Internet of Things deployment. Okay, this is the data transmission in 10 rounds. So this is the rate of data transmission as regards to the implementation of the model. Then this is also the byte transmission in megabyte. It's a typical illustration. The estimated communication overhead in megabyte transmitted for federated learning round. Then table 3, classification metrics per class for crop disease status. The table 3 and figure 5 shows per class classification metrics with precision recall and F-score exceeding 0.90 across all crop disease status categories. This balanced performance highlights the model's robustness in accurately detecting varying disease status. This finding confirmed the federated learning framework's capability to deliver reliable crop health monitoring on resource-constrained renewable energy-powered ESP32H device supporting practical precision agricultural applications. This balanced performance highlights the model's robustness in accurately detecting varying disease status. This finding confirmed the federated learning framework's capability to deliver reliable crop health monitoring on resource-constrained renewable energy-powered ESP32H device supporting practical precision agricultural application for wide-scale deployment. Then this is the classification metrics per class for crop disease status as reported in this research. And this is the graphical visualization as a matter of the crop disease status. You see? So result and discussion further. System level evaluation on the quantized model indicates significant deployment efficiency. The model size was reduced from 320 kilobytes to 25 kilobytes, enabling storage within the ESP32 flash memory. The average inference latency was under 0.375 ms, facilitating real-time decision support in the field. Conclusion and future works recommendations. This study demonstrates the feasibility of implementing federated learning on resource-constrained ESP32H device for precision agriculture, achieving up to 99% accuracy in crop disease detection with low communication overhead. Model quantization reduced the model size from 320 to 25 kilobytes, enabling efficient on-device inference with sub-milliseconds latency suitable for resource-constrained off-grid environments. Future work includes deployment through hardware prototyping with solar integration, real-world performance evaluation to assess energy efficiency, inference latency, and communication robustness, as well as enhancement via adaptive communication model compression, multimodal data fusion, and fault-tolerant algorithm. This is the references. Of course, with this point here, we have successfully come to the conclusion of this presentation. Thank you very much.
Thank you, Matheus. Thank you. Any questions? Any question for Matheus? Yeah.
Okay, I can entertain the question.
Any question? 1 minute.
Thank you so much for the presentation, Matthew. And I just wanted to ask resource constraint using ESP32 graphs. One is in your data collection, you mentioned that that was the did you actually collect the details for the use and existing data? Then the second is using ESP32 graphs was the model already deployed on the ESP32 or the deployment will be these are the solutions that I think.
Okay.
Please, pardon. Can I get the question again? The echo in the background was actually preventing me from beginning the question accurately. Please, can you repeat the question again? Don't be offended.
Okay, can you hear me now?
Yeah, I can hear you.
All right. I said there are two things I have to make in my presentation. One is integration data was collected from 500 banks for training. I want to know if this collection of data is self-developed or you use an existing training model. And again, the title of the paper is using ESP32 device. I want to know if the algorithm was trained deployed on the ESP32 or is deployed in the future. And what algorithm actually, maybe CNN network, what channel use in training the model?
Okay. Okay. If you look at the general concept being promoted in this research paper, it is an aspect of precision agriculture where we deploy a state-of-art technologies. So, if you look at the data set that we are used to implement this model, So we included the environmental factors, looking at the humidity, the temperature, and other factors, even the soil type. So this data set we analyzed and peculiar issues with them were also put into consideration in order to determine the cost effectiveness in implementing this model to enable an improvement in crop yield, because the essence of the whole of this is to have an improved crop yield. So we deploy a state-of-art technology that could be able to analyze the environmental factor as it regards or is peculiar to certain crops. So having analyzed this factor, we're able to detect the effect of growing such crops in a certain area, in a certain environment, with the peculiarity of the environment. So when this is analyzed and deployed within this framework we implemented here, so we discovered an improvement. So there was improvement when deployed on this ESP32 as a matter of fact. Moreover, ESP32 is a device that operates on low cost, low power microcontroller developed by Express If system that they use in Internet of Things application. So this ESP32 is just like a device that is peculiarly adaptable to Internet of Things application. So we adapt it within the context of precision agriculture. Then with the data set being analyzed within this study, so we're able to communicate. If you look at the graphs and the tables and the important operation performed, you'll be able to see a consistency, also effectiveness as regards to data interpretation. I don't know whether I have answered your question based on your observation.
Okay. Okay, thank you, Matheus. Thank you for your answer. Now it's necessary to close the session. Thank you very much for attention, for participation. See you tomorrow. Okay? Congratulations,
Yeah.
Matheus. Bye.
Thank you. Thank you.
Bye. See you tomorrow. Muito obrigada. Por hoje encerramos. Amanhã continuamos. Tá.